My name is Lalit. I'll be presenting about how we use Perfetto tracing inside Google to analyze traces at every possible scale that you can imagine. So a little bit about me. I have been at Google for about 5 years. I also interned at Google before that point. I joined Perfetto as it was founded, having worked on memory infra and Chrome for a little bit, and then since basically 2019, I've been working on trace analysis aspects of Perfetto, and also collecting traces from Droid-free devices, so the devices run by internal Googlers testing the next version of Android. It's kind of the agenda for today. I'm going to try and give an overview of Perfetto and Trace Processor. Premiano has kind of already given you that yesterday, but I'll go into a little more detail on the Trace Processor aspect of things that he didn't cover as much. I'll give you an introduction to Android app startups, which will act as a very useful example for the remainder of the talk. And then I'll show how you can how we analyze traces in local debugging use cases, in lab tests, and also in field tracing. And I'll finish off by talking about the latest innovations that we're doing in this space. The basic goal of the talk is to give a sense of the variety of domains we operate in, and the similarities and differences kind of in each domain. The talk is intentionally going to be quite fast-paced, so feel free to grab me at any point to discuss stuff in more detail, or in the unconference session. Let's talk about the foundations, which is the Perfetto and Trace Processor. So Premiano kind of already presented the slide to you yesterday. Perfetto is a suite of tools to help you record, analyze, and visualize traces. Premiano focused mostly on the recording part. I'm going to be talking mostly about the analysis and a little bit on visualization as well. A refresher, so Perfetto, as I said, is targeted at local debugging, lab testing, and dynamic field tracing. All three of those cases are well supported and battle tested inside Google. So specifically for both Android and Chrome, who are two of our primary users. Trace Processor is the analysis engine for Perfetto traces. So Perfetto traces are kind of optimized to be very fast to write, but not so much to query and do analysis on. So the job of Trace Processor is to take in a trace and then provide some sort of interface to allow efficient analysis. We support up to multi-gigabyte traces. I think the maximum we've ever tested on is a 21 gigabyte trace, which spanned multiple hours. It's all SQL powered, and I will explain why SQL is such a good language. And I'm very happy to see that other people in tracing are also using SQL in different ways. It's extremely interoperable and embeddable. So specifically, we embed it in all sorts of random tools, and anywhere you kind of want to do some sort of performance debugging with Perfetto, Trace Processor is probably hiding somewhere along the way. So the four key areas of highlights, I guess, for features in Trace Processor are the parsing and data massaging, which is the job of turning the complicated intern state, or a lot of the trace format, which is written to be efficient to write, into the most massage it into a format which is efficient to query. There's also a homegrown custom in-memory columnar tables. So specifically, SQLite is optimized for live database transactions, and not really so well for as an analysis side database engine. So this really helps with this, and it's crucial for the use case of embedding Trace Processor inside the Perfetto UI. Where as the user scrolls, we're actually doing live queries to kind of get the latest state of the trace. It's an SQL API, as I said, all powered by SQLite, so it's well tested ground, nothing too special there. And there's built-in metrics for Android and Chrome. It's kind of batteries included sort of approach, so that developers can get what they are looking for without needing to necessarily write stuff themselves. let's look at data massaging first. So in terms of data massaging, the idea is that we're turning the instrumentation that it was demoed yesterday of trace begin and trace end into what we call a slice, right? So we're computing the duration of the slice, and then also stuff like the stacking depth. So if a slice is nested underneath another slice, then we also compute that inside trace processor, so that people don't have to do that themselves in SQL. We turn all sorts of variety of counters into the counter table. So this is the idea is that any sort of counter-like thing can be turned into put in the counter table, and it's basically just given a value. Finally, we have I guess the most kind of relevant to this audience, but also the most complicated one, which is something like thread state, where we're combining data from sched switch, ftrace events, and sched waking, and sched blocked reason, which is an Android specific event, into this thread state table. And the idea is that we're giving an overview of the running the state of every thread in the system at every point in time. And this is used by the UI to draw kind of the things that you saw yesterday. And also another important thing is that when we say that it's an SQL API, it's not a pure SQL only API. There are some things which undoubtedly it's very hard to do inside SQL. A key example is something like span join, and this is it's very common to require an intersection between two things. So let's say, for example, you want to intersect, you want to compute the megacycles of a process, and you're trying to intersect scheduling data with CPU frequency data. And so you want to kind of intersect those two and then multiply the frequency by the duration of the scheduling state, right? So that sort of thing is very hard to do in SQL, but we basically define C++ operators to let you access SQL, access this from SQL without needing to write that code in SQL itself, right? But it's like low-level primitives is essentially the name of the game to help you write queries easier. There's also the ability to create functions in SQL, which is SQLite doesn't have this functionality, but inspired by things like Postgres, you can define functions in SQL. And I'll show you an example of this later. And also things like ancestor and descendant. So like walking up and down slice stacks, something very common, especially Chrometrics do this a lot, where they're like going up the stack, looking at the top level slice, and then going down the stack, and so on. So trace processor is actually, there are many layers to trace processor. So at the heart, it's a C++ library, which is embedded in all sorts of tools. But there's also a shell, like a command line shell, which kind of embeds the library and provides like some sort of interface for writing queries on the command line. But the command line often isn't necessarily where you want to be, and so we also have like a Python API, which is, you can think of it as like a binding around trace processor shell to provide you access to writing queries, etc., in Python. And I'll show you how you can kind of combine visualization and queries very nicely in Python. And then batch trace processor is a tool. There was a question yesterday about how we look at multiple traces in aggregate. Batch trace processor is our answer to that, where you can analyze up to several thousand traces interactively live and query them kind of in parallel. This is something I'll discuss at the end of the talk. So there's a few, I can already kind of predict that there are some questions in your head about why not do X, where X is whatever. So three of the most common things that have kind of come across in the past is why not why not look at the trace file directly? Well, the answer is, as I said, traces are very efficient to write, but not necessarily query. So Perfetto traces, for example, have what's called interning, where you can emit a string once at the start of the trace, and then instead of emitting the string again throughout the entire trace, you just emit an ID which references that string. And so kind of trying to do this, everyone reinventing the wheel here would be complete pain. So trace processor takes care of that for you. It does de-interning everything transparently. The other question is, why not expose like the raw trace points? Why are you massaging the data at all? Maybe people just want to look at the raw data. My kind of answer to that is, if you're a kernel developer, maybe that's true. You actually care about the trace points. But for the average developer that we're kind of targeting, which is your average Android engineer or your average app developer, let's say, right? They don't really care about the details. All they care about is my thread running? Is my thread not running? That sort of thing, right? So it's better to massage data into that format. And then finally, why are we using SQL? And the question, I would return that as another question, which is, try and do this in C++ without having oodles of code, which is doing everything that you can imagine under the sun to do with databases. And you'll very quickly find you've reinvented a database if you try and do this. So I would actually argue, why not SQL? Because I think it's the most natural way to express language like this. Well, a query like this, let's say. So let's have a look at app startups, because they are a very important use case for this sort of thing. So app startups are complicated. That's basically the takeaway from this slide. There are a lot of moving parts, cross-process, IPCs everywhere. Multiple things are involved in making sure that an app starts up quickly. And this is already out of date. People change how app startup works like in every version of Android. And so understanding what is the system doing is absolutely critical to make sure that we're not launching. It's not taking seconds to launch apps, which, quote, spoiler, it does actually happen. Which you might not expect. So the two critical things for app startup are there is a slice in a process called system server, which tells you the package which is being launched, and then then there's the process which is actually being started. And then there are a bunch of slices which give you the kind of detailed breakdown of what that process is doing. The critical thing to focus on is let's try and extract the critical pieces of information from app startup. And this is what app developers kind of care about the most, let's say, right? Which is how much the process name, and then how much time was spent in the 3 top level slices. And so what I'm going to show you is kind of how you might envisage doing this in trace processor with SQL. So let's start off by first getting the launching slice from the trace. So this is how you kind of write that query. I'm creating a view, and I'm extracting the package which is being launched, right? And then I'm matching on this pattern, on this glob pattern. Next, we can get the process, which is associated with that launch. And all I'm doing is looking at the process table, which is a table built into trace processor, which gives you information about all the processes on the system, right? So all I'm doing is getting the process name, which matches the package which is being launched. Next, and this is the example of creating a function in trace processor. You can basically say, okay, like I want to get a duration for a slice, and for a given process name and a slice glob, right? So I'm going to say, okay, give me the duration from this thread slice table, which gives you access to the slices associated with a thread, as you might imagine, and where the process name is X, and a slice name has this pattern, right? And this is how you create the final result, right? So you basically say, I'm gonna extract the data from the launching processes table. I'm gonna get the process name, and then I'm gonna use the function to compute the activity start, resume, so on aspects of the startup, right? And this is actually going to generate a proto. We also have proto builder functions in SQL where you can generate a protobuf directly from SQL without needing to write any glue code. So this function call of the startup proto metric is actually creating the proto. And this is what that looks like on the output. So I ran this on that very trace that you saw. So all the code here you can actually run and test this yourself. And you get a metric which looks something like this, right? So, and this is the kind of a basic building block which we use throughout all the other aspects I'm going to explain in this talk. So let's take a look at local debugging and how we use trace analysis there. So demo the Perfetto UI. It's a great way of kind of visualizing a trace. But what he didn't show yesterday is that there is this tab called metrics, this tab called query, sorry, which lets you write SQL queries directly in the Perfetto UI. So the same sort of query that I showed, you can write, like, select from the slice table where launching is this, and in a nice tabular form, you can see the slice the same slice. And actually, you can click on it, and it'll jump to that slice, for example. Next, we also have this metrics tab, which computes the startup metric, which is, I guess, a more full-blown version of the kind of the toy metric I showed here, right? And this contains all the different information that an app or a platform developer might care about startup. Exactly the same thing can also be done in the command line with trace processor shell. And this is how we integrate it with kind of all the other tools. And you can do the same thing with C++ in the C++ library as well, if you want to call it from some other C++ system. So yeah, again, you can query the same thing, and then you can also query and get output as CSV. And this is useful if you're going to pipe this into some other tool, like, or visualize it in like a spreadsheet or whatever. And you can also, of course, also compute metrics from the command line as well. It gives you exactly the same output in the UI. Because trace processor is under the hood everywhere, you get consistent metrics no matter where you go. So Android Studio does the same thing. It can compute the same metric as the Perfetto UI as some of the internal systems that I'll show later on. So lab testing. Lab testing kind of works like this in Android. So a commit is merged, and a build is generated from that commit. And then what we do is we run performance tests on which are associated with that commit, like somewhere between 50 to 100 times. And we kind of compute, we collect traces from each of those runs. So every run has its own trace. So you might end up with 50 to 100 traces. You run every one of them through trace processor and then extract the metrics from them, the same sort of protobuf metrics that I showed you. And then you do some aggregation on those metrics. So you like sum them or average them or whatever it might be. And then then you can store that in some sort of metric time series system. And this is kind of how we this kind of one of the dashboards that we have internally for the calculator app, which is tracking the app startup time over time. And you can see, okay, there's some regression, and then you can feed that into your normal alerting tools and kind of the regression detection sort of systems, which are you might be used to for metrics, right? And then the advantage of doing this rather than collecting the metric directly from the system is that you can always open a trace before and after and then compare the two, which you can't do, obviously, if you collected it from the you collected the metrics directly and you didn't collect traces, and this is the advantage of trace-based metrics. Now let's take a look at field tracing. Prumana was going to show this in his talk yesterday, but this is one of the slides he ran out of time. I have replaced Jank with startup because everything still holds, because they're basically the same thing. All of these problems are kind of very similar. So where you start is, of course, you have your problem space, and you need to kind of measure high-level metrics, so always on 24/7 metrics, which give you a sense of what is the actual state of the system, because you need to know what your users are seeing. If you don't know what your users are seeing, then you're optimizing blind, right? You don't really know what you're doing. Once we've observed that there is some problem in the metric, then what we can do is we can actually trigger the collection of a trace. And then this is from real user devices here. So we have the ability to collect from Google employees. We have the ability to collect field traces. And then what we do is we analyze those traces running through trace processor, as I showed. Then you have basically classifiers, right? So you generate classifiers which kind of rank, which extract different facets of the problem. So, for example, the trace might demonstrate slow startup because of bind application being slow, that aspect of startup being slow. And so you want some sort of classifier which tells you, hey, what is the threshold for bind application being slow? And then you tag that trace with that classifier, right? And then you kind of stack rank those issues. You focus on the issues which matter the most, and then you fix your top issues. And hopefully that will generate some sort of useful that will generate a drop in the metric as well, because if you focused on the right problem, fixing that problem should also generate kind of gains in your actual metrics. This is an example of the classifier from the startup metric, which is in the Perfetto repo to this day. So you can see, what we're doing is a lot of the pattern in this metric is we extract some facet from the startup metric, and we say, okay, this is the threshold that if we expect it to be greater than this value, then flag this as a problem and tag this trace with this problem. And how this looks like in practice, yeah, and I'll show how this looks like in practice in a bit. But this is kind of how it works, right? So in Google, once you get beyond a certain scale, everything becomes a MapReduce, and this is no different. So what we do is we have like 30,000 traces or something that we process per day, and then we feed those traces through Trace Processor. So we have a big MapReduce pipeline, which basically maps the traces into metrics, and then we reduce those metrics into a giant table, right? And then we can query this table, and we can run kind of analysis on this table. We can dashboard the table, etc. And I'll show some of those dashboards later. And this is what an example of the dashboard looks like, right? So you can see there is all the packages being started up. Every one of those rows is a trace, and you have the information about the metrics extracted from that trace. And then these are the classifiers, the same classifiers that I showed you earlier that you're seeing, which are kind of tagging the traces with these problems. It's kind of horrifying, but there's like a 16-second startup here, which it's probably a big problem. And in this case, it's probably because of I/O on the system. There's some massive edge case. You would never detect this in the lab, right? You would never see 16-second startups in the lab, but clearly in the field, this sort of thing does show up every now and then if the system is in a really bad state. We did exactly the same thing for Jank, and this is, I guess, Jank was earlier. We did this earlier for Jank, so we're actually seeing the results of that. So Jank, different classifiers, but very similar approach. And this is actually the real-world results from this. So our higher-level metrics actually went down. So for example, going back to the home screen went down by a significant percentage in our high-level metrics. So this sort of approach does yield real-world gains in performance. So let's talk a little bit about the latest innovations. One big thing that we've wanted for a long time is, can we interactively query more than one trace? So everything I've shown you until now, like you're interactively querying one trace in the Perfetto UI or in Trace Processor Shell, but that's not useful if you're trying to get patterns, like you're trying to see what the patterns are across multiple traces. And then you've got your MapReduce style pipelines on the other side, where they can run over like tens of thousands of traces, but it's extremely slow to iterate on these pipelines. Like startup cost is very high, and you need to recompile the binary every time. So the kind of what we were trying to do is, can we find some middle ground? Can we find some ground where we can interactively query traces, but we also have like the full power of Trace Processor, and we're operating on like let's say like 100 to 1,000 traces. So we're getting a representative sample of like 30,000, right? So the solution that we came up with was a project called Batch Trace Processor, which, as I demonstrated earlier, is just a Trace Processor shell wrapped in a Python API, which is itself wrapped by Batch Trace Processor. So the idea is that we load, let's say 100 or 1,000 traces in memory in parallel, and then we're basically, when we write a query, we're going to issue the same query to all 1,000 traces, and then we aggregate the results into a table that you can analyze. And the traces can come from a lot of places, so it can be from your file system, but it's also deeply integrated with Google internal systems. So you can directly get traces from, like let's say the Droid Food traces, or Android like CI infra traces, for example. And the architecture is pluggable, so you can put in your own like kind of trace source, let's say. So this is kind of how it looks like in practice. So you can write queries in Python, and then you can chart information. And this is from, if you've ever used IPython or Google Colab, this is an internal version of that all of this is based on. It works as a standalone library, but the real power of Batch Trace Processor can be seen in these sort of code plus visualization settings, where you can write some code and then see the visualization right below. So for example, I'm extracting a slice and I'm plotting a histogram across 100 traces, right? And this is way more representative than if you looked at a single trace, and you get very smooth histograms, whereas if you had this in a single trace, you would get a lot more noisy data, let's say, right? And this is very useful for finding like, okay, what is the threshold that I want to set for my classifiers in field traces, for example. So now I can show quickly what this looks like for two collabs that we built for Jank and Startup. So can we switch to my laptop? Great. So yeah, so what this actually is this is this is the 50 to 100 runs that I was talking about earlier, and this is a regression collab. So the idea is that we're trying to understand why a metric regressed. So in this case, startup. So startup regressed by in this case, Jank. So there were more janky frames, or the frame time was longer in the regressed build. So on the left you have the 50 runs from the baseline, so the good case, and then on the right you have the regress case, so the case where it's higher. Right, and each of these charts is different processes. So this is the surface flinger process, this is system UI, and this is the launcher. So one quick thing which jumps out by looking at this chart is that you can see that there's slightly more jank in the regress case, which is the red lines here. So you can see, on average, it looks like there's slightly more red lines here. Right, and then if I scroll down a little bit more, you can see this very obviously in this case, which is, and these are like frame time plots. So each of on the x-axis again, you have the runs, and on the y-axis you have the frame time, so the time taken to render that frame. And you can quite clearly see, if I go to the regress case, there's way more frames which are kind of taking way longer, right, compared to the baseline. And so you can see stuff like bimodality in these charts. So you can see, okay, like is the frame times, is there a consistent pattern in some frames taking a lot longer? And if I hover over this, you can see, okay, like which frame that was and why that frame was classed as janky on the device, for example. And then we have detailed breakdowns for various slices that a platform developer might be interested in. So specifically in this case, okay, like animation took a lot longer on the regress case, and that might be something that gives you an insight into where the cause of the problem is without needing to actually open, like I haven't even opened a trace here, right? So like I can get a lot of information by not even opening a trace, and the advantage of this is that I'm getting information from 50 traces rather than looking at a single trace, for example. Another example is startup. So this one is even more kind of clever because it almost gives you the reason why the startup is happening without even like necessarily needing to interpret charts. So in this case, you can see, okay, startup regressed by like 50 milliseconds or so between two builds. And it seemed like there was a bunch of slices where the running time took longer. And generally speaking, this is like, okay, there was like some kernel patch which made running like the CPU frequency slower, or there was something else running on the system which was causing the running time to take longer because there was contention. That's usually the cause of something like this, right? And again, you can get this sort of insight without even opening a single trace. And you have various charts which break down various aspects of startup, right? This sort of thing has proved very useful for triaging regression bugs much quicker than we were able to do before. And I think, can we switch back to the slides? So that's Jank and Startup, and I think that's it. That's all the content I have. I know that was a lot. Sorry about that, but I had a lot to get through. So yeah, thanks a lot. Any questions?
Hello. Yeah, that was a very interesting talk. Thanks for that. So I'm trying to piece together. So I think you showed a slide with three possible things. One is Perfetto, one is your MapReduce, and the thing in the middle is your batch processor.
Yep.
But what I'm trying to figure out for MapReduce, I think the output isn't a table that you SQL. So, and I think the batch processor is giving you that capability. Did I understand it correctly? Like, it gives you something you can query using SQL, or did I misunderstand?
Yeah. So the MapReduce is very fixed, right? So the idea is that you have some metric that you want to compute over every single trace that we collect, right? And the idea is it does end up in a table. So if I go back, I can show the slide where like I showed them what actually happens in MapReduce, right? So which is this one. So you can actually see like each row there is a trace, right? And then you're seeing the metric for that trace, right? And this is a table that you can then query using like Google internal SQL.
Yeah, but that's not but that's not as productive because the queries that you could do with SQL
Yeah.
and do your own intersections, compute ad hoc, sort of do analysis, right? Instead of MapReduce requires me to build a lot of stuff. And
yes, and that's the critical thing that batch trace parser allows, which is interactive queries with second query time and no compilation required, right? So because everything is in memory and hot, then queries are essentially instant.
So it gives me the same UX I would get with working with queries on
yes, that's right.
Single trace. Okay.
Yeah, it's literally like imagine you had the power of 1,000 UIs in parallel, and that's kind of what it gives you, right? Yeah.
Very cool.
Cool. I think we had another question on the other mic.
Yeah, I just have a quick question about the SQLite. So the function support, is it provided by the database or
Nope.
post-processing?
Yes. So the create function, create view function, those two things are trace parser specific. SQLite does give you the ability to write functions in C and hook them in, or C or C++, and hook them in, but that's not useful because then you need to recompile, right? You really want something like Postgres, which is where the inspiration for it was drawn from, which they let you write functions in SQL and call them in SQL. And the create function is a trace parser equivalent of that, which is doing the same thing. It's letting you define functions in SQL for SQL.
Break, and then we'll be on to the next talk.
A big problem we have when we get regressions like you showed in the production data is assigning actionability, figuring out who broke this, when, and why.
Yep.
What tools does Perfetto use for that? Do you grab stack traces? Do you attach metadata like experiments or other changes that recently happened to figure out what caused a regression?
So that is kind of partially out of scope for Perfetto, like in the sense of what we're trying to figure out is how the traces are different, right? And so that's what the collabs give you. They give you a sense of this was the kind of the thing in the trace which changed between like build A and build B. In terms of finding the CL, you need something on top of that because you need something that maps the change in the traces to the CLs that change, right? And that's not that's not an easy problem either. So in Android, for example, regression bugs give you the list of CLs between the two builds. And then historically, what people have done is they've opened 3 traces from baseline, 3 traces from regress. They've manually compared like the Perfetto UI in each of those traces to see what the difference was. And then what they do is once they know that difference, they look at the list of CLs and they say, okay, like this is the one which probably looks like it's related to why it regressed, right? And that's not like what these collabs are trying to do is go for an approach where you don't have to open traces necessarily. You can just look at the overarching view and then you get a sense of this is what changed, and then you can look at that CL list directly.
One thing we've been experimenting with is taking very lightweight stack trace snapshots along with performance traces, just so we can say roughly who owns what area that the trace is involving. So maybe if it's not a specific CL that's broken things, but over time things have gotten worse and worse and worse, and team A, B, and C are all involved, it'd be nice to say, oh, 40% of the blame is team A, 30% is team B, and 30% is team C.
Yeah, so for that use case, what we do is we collect stack samples in DroidFood, and then we aggregate them across like the entire population, right? And then we focus on like the functions which are like the worst, let's say. This is especially for power, like we do a lot of this for power, but also like, just saving CPU cycles for sure is always good, so.
Thanks, Lalit. And